forests, silver, mines, pumps, and the Royal Society. This lecture has 4 parts. We're going to review. We're going to look at 9 significant global changes that contribute to the scientific revolution. We're going to look at historical thinking and philosophers who contributed to the scientific revolution. And we're going to look at the British Royal Society, which was founded in 1660. And yes, that was my cat. In our very brief tour through the Renaissance, we looked at practitioners of the arts and sciences like Leonardo da Vinci, Luca Pacioli, and John Dee, who all had a foundation in math. New maps for navigation and new and accurate recordings of anatomy were created, and also they were spread through the printing press. Wealthy people had an interest in collecting exotic species of animals from the New World, but for the ordinary person, something like access to salt was more important than gold or silver or monkeys or math. Most people had humble goals, like surviving to the next winter. This period saw the addition of the Americas to the European maps, and it also saw the conflict between major organizing ideas about where our world actually is. It heralds the beginning of the telescope, one of the essential instruments of science. It also heralds, although I didn't talk about it in the last lecture, the printing press, which we will address in this lecture. There are 9 significant worldwide changes that affect the scientific revolution. First, we move from a higher population to a lower population and then slowly start moving back up again. Then we go from a warm climate to a cold climate. We have new sources of high-value metals, and there are new staples, potatoes and corn, that move across the world, also new diseases. Then there's the print revolution. Moving from manuscript to print is huge for the scientific revolution. And then there is a unified Christian church which is broken apart into 2 major segments, and there are wars surrounding that. Then there is a slow growth of larger towns, and we think of moving transportation from primarily rivers to rivers and roads. Last but not least, we have new developments in weaponry and, as I mentioned, war that really affect this period. As you know, the unintended consequences of European encounters in the New World were decimation. Diseases that indigenous people had no experience with and no protection from killed entire villages and emptied out the coastlands. Forests that had been cleared in both North and South America grew back over. And hey everybody, sorry, my cat's on the desk here and he's complaining that I'm interrupting his nap, so you're going to hear him off and on throughout this lecture. Okay, Europe also paused its growth in several places due to war and famine in what is present-day Germany, France, and Spain. The world was mostly rural, but by the end of the century it's well on its way to being urban. And I've marked this slight downturn in the period where we're talking about, where there's a static spot in European city growth because of some of the population issues, we'll call it. And the actual statistics are kind of sad. And in the notes I've highlighted some things that stood out to me. Over a 50-year period, the European population actually rolled back 4 million people. England and Holland were kind of okay. They just about doubled in population, but the rest were not so okay. Because of the 30 Years' War, there was a downturn in Germany, Italy, and Spain, and particularly it was devastating for Germany. Now, I've got a really fun look at European demographics through city populations, which is linked in the notes. It's just kind of fascinating to watch cities flicker and come forward and drop back again. Rome in particular is quite fascinating to watch, so you might want to do that. Okay, the next thing you need to know is that the whole world experienced a period of cold lasting from roughly 1400 to 1800. It was underscored by a lack of solar activity, which is called the Maunder Minimum. And that happened between 1645 and 1715. And the Maunder Minimum means basically there weren't very many solar flares or any solar flares, and so the world just stayed colder. Also, at the same time, there was an increase in particulate matter in the air. There were a couple of volcanoes that went off in South America and East Asia. And together, the Maunder Minimum and the volcanoes brought the world average temperature down by about 2 degrees, which doesn't sound like a lot, but it was a lot. Winter was just miserably cold for people who barely had enough to eat or enough fuel to stay warm. And that's 400 years. That's a long time. Now, some scholars have also argued that the depopulation of the New World increased the forest cover in North America because the indigenous people had cleared that off and then it grew back over. And the forest cover put less CO2 back in the atmosphere, and that also contributed to a colder planet. So there's some human-caused changes as well as these what we'll call natural changes going on. Although, as we said, the world was colder, Europeans didn't sit at home. They were still out sailing, looking for trading partners, access to spices and silver and gold. And once Europeans located silver in the New World, the die was cast for a serious attempt at New World domination. This is the cover of a publication which describes the Spanish conquest of Peru and the silver mines at Potosi, which I've got pointed to in Bolivia there. Beginning in 1503 and peaking in the 1590s, so that's about 100 years, gold and silver flooded into Spain from Central America, Mexico, and Peru. The silver mine, which was discovered at Potosi in 1545, went from no population to 120,000 in a blink. It became a city and a slave city the size of London or Paris, with just misery and squalor at the highest altitude of any city in the entire world. It's a terrible reason to be famous, but so it was. Europeans designed a new technique to use mercury vapor to mine the silver, which allowed for a much more efficient extraction of silver and encouraged these massive scales of work, as well as, unfortunately, because it was mercury, sickening and killing the miners themselves. And I've put in a few links about that if you're interested in learning more. I've got a quote in here that tells you from some specific studies that the mercury that was put into the environment at that time in the 1540s still obtains today. It's still evident, still detectable today, which is kind of awful. Well, the silver that was going to Spain didn't stay in Spain. It was desired by the Chinese, who had a great shortage of valuable metals themselves, and they needed it for their economy. So silver suddenly tied the world together. People living in Peru, locals and slaves who were brought there to Peru, were suddenly working so that the Spanish could pay for goods that came from China. So there was a growing and a yearly trade between the Spanish and the Chinese that sent treasure ships loaded to the gills to the Philippines, where they exchanged silver for finished Chinese goods in silk and in porcelain, which then came back on these overloaded ships sort of wallowing back to Spain. And if you're interested in what they look like, this is an actual gold bar that was mined by the Aztecs on the left there, and on the right is silver that was mined by the Spanish in Potosi. Well, why do I have this particular bar of silver to show you? The silver didn't all get around from Peru to the Philippines. This is a bar that was recovered from a 1622 wreck of the Spanish ship Atocha off the Florida Keys. You can see the date, you can see the owner's mark, you can see the grade of purity, and the assayer's mark. I was really surprised, almost astonished, to learn that the Spanish dated and assessed and tracked silver almost the same way that, with a database mindset that we would have ourselves. And if you want to look at this a little bit further, you can look at the seller's website, which is kind of fascinating. We've covered the persistent cold, and we've alluded to the 30 Years' War, and we've talked about the rapine and plunder that was silver mining. But again, let's think about the meeting between the Old World and the New and what it did to the Old World. There's a great biological mixing between the continents that had been separated for eons. Suddenly, people on both sides of the planet had choices about what to grow and could try things that might fill in their gaps or their needs. Corn and potatoes profoundly changed the food landscapes for everyone living through lean times in other parts of the world. Just for example, American sweet potatoes became a staple food in China. The Egyptian national dish has tomatoes in it as a garnish, so you have to know it's not really an ancient Egyptian national dish, it's a more modern national dish. So we've talked about high population to lower populations, a warm climate to a cold climate, new sources of high-value metals, and new staples. We're now going to look at manuscript to print, going to a fragmented Christian church, talking a little bit about larger towns and rivers moving to roads, and weaponry and war. So first, these social changes include the printing press. On the left, is a broadsheet attacking the Pope. It's an early example of print culture and what it could do. The caption is Ego Sum Papa, meaning I am the Pope. And this Pope is actually Alexander VI, whom I mentioned to you as one of Christopher Columbus's buddies. Right? He's imagined here as a kind of a horrible demon. Unfortunately, he actually was a pretty bad Pope. Even so, though, and we all live in an era of very trollish social media, I still think this image is pretty awful. It's startling, it's disturbing, it's kind of nasty. So you can see that people were willing to put in images what they wanted to say about each other. On the right-hand side is an image of the Gutenberg Bible, which is located in Texas, this particular Bible. So think for the first time that information, any kind of information, can be located on the same page. You can print it so that anyone, anywhere in the world can turn to page 20 and be looking at the same thing. That's new. The printing press brings that together. Everyone can find something, they can see it, they can check it, you can circulate ideas. It's a huge change in the dissemination of information. And if you want to take a side dip in lecture on books and bookmaking, I've got that linked in the notes. Just have a look at the growth of printing on the image on the left. It just took off like wildfire, kind of like the cell phone or the internet itself. And it seems to me that there's some common threshold moment in society when the demand for information almost takes on a life of its own. It isn't entirely logical or predictable. In fact, you can remind yourself that it would have taken 3 years for some new customers to have learned how to use the product. That is, adults are learning how to read. They may not have done that really quickly. So it's kind of astonishing that things really move so fast. So there's a creation of a readership for printed books, and it's kind of broken out at this point. Now, on the right, speaking of breaking out, look at the breakup of the Catholic Church across Europe after the Protestant Reformation. There's pockets and areas of Protestantism scattered across the map. Essentially, there are places for dissenters, whether Catholic ones or Protestant ones, to gather, to talk, and to think. There are readers, and there are spaces to be a dissenter. And that, taken together, that's a new thing in European society. I want to recommend a website called Our World in Data. It's a fascinating site with a fascinating agenda to prove that the world is actually getting better. Now, that actually seems unlikely to me, but these guys are cheerfully determined to show it. And it's a good exercise in asking what historical facts are truly significant. So there are two other things to think about. Urbanization sputtered and then it started up again. But the group of people who could pull taxes from the population and could command cash to pay for labor mostly lived in cities. The people who relied on successful farming to eat lived in rural locations. The world is coming together in cities, and the future scientists are gathering in cities. And as I said, this graph comes from Our World in Data. Another point about social change in landscapes. Governments are investing in roads. True, they're not great roads. Anyone using them still goes at horse speed or foot speed. But from 1765 to 1780, the time it took to travel across France, for instance, was cut in half. Now, trains came 40 years later in the 1830s. Now, previously, as I indicated, people would use waterways or as their travelways. Now they could legitimately use roads. If you think back to our overview, one of the problems that I didn't list, but it's a big one, is how will we control other people? It's not a problem for the people who want to do the controlling. It's definitely a problem for the people who are being controlled. Well, in front of you here is a firearm that was developed. We mentioned that firearms come from China and gunpowder comes from China. This here is one of the end products. This is called Mons Meg. It's a cannon that could fire a cannonball 2 miles. I happened to run across this in Scotland. I was traveling there. I was visiting actually to do research on the portrait of Margaret Tudor, who has the marmoset in her hands. I was really interested in how that came to be. And so when I was in Edinburgh, I went to this castle. And when I was at this castle, I discovered that this particular cannon, which I had read about long ago in grad school, was actually still in existence and right there. So that's a cannon that could throw a cannonball 2 miles, and that tells you something about how weapons and weaponry were developing. This is a woodcut of the Siege of Magdeburg in Germany in 1631. Magdeburg changed hands 10 times in the vicissitudes and the terrors of the 30 Years' War. That's the war between Protestants and Catholics. It's a mess of a war. It's difficult to explain clearly because it has several stages and many countries going from enemies to friends and back again. Overall, though, it was devastating in its effect, and you can see these cannons as they're firing against the city. I actually include another lecture on this if you really want to know more. Eventually, cannons became lighter and deadlier, and they could be mounted on a movable platform, specifically on a ship, and they could rain explosives against coastal cities and coastal citizens. And the ships changed accordingly. They became stronger, heavier, able to carry double decks of cannons. And in this case, in the cases that follow, we can say that science is expressing itself as technology and weapons technology. Ships like these are part of the English Civil War. Now the English, although they had a population growth, they didn't escape the turmoil of this period. In protest against the taxes that were levied on them by Charles I to pay for ships like this, and for other issues too, they revolted. They beheaded Charles, and they established a brief interregnum with Oliver Cromwell as the head of state, before thinking better of monarchy and inviting Charles' son, Charles II, to come back home. And that'll be important in a minute. But let's finish the cannons. These are the kinds of changes that the cannon made to castle fortifications. Castles needed to have these angled bastions or rounded walls, one or the other, to allow defenders to fire in several directions. And they needed to have thick, low walls to resist cannon fire. They couldn't be as tall or fragile anymore. On the left and on the middle are there two views of Cupertino Castle, which is on the Boot Hill of Italy. Now in the upper right is one of my favorite forts, A Famosa. It sat on the Malacca Straits, and it was built to protect that worldwide trade that we were talking about. That's a strait where everybody would go through who were trading. And it was built first by the Portuguese, who got there first, and then it was taken over by the Dutch, who edged out the Portuguese, and then it was taken over by the British, who edged out the Dutch. When the British decided to leave it, it was so heavily fortified, each owner had improved it and fortified it more, that they didn't dare leave it behind, and they didn't want to have it unguarded, a big heavily fortified fort for an enemy to take. But they couldn't actually knock it down. It was so well built they couldn't get it down. So they had to blow it up with gunpowder, and they had to use so much gunpowder that they pretty much half blew it across the Malacca Straits. So there you have it. That kind of made me laugh, although it's rather sad. So we have looked at the development of weapons, of the printing press, and of roads. We didn't directly talk about empire, but the succession of Portuguese, Dutch, and English tells you that each nation-state was trying to take territory somewhere else. We also noted that the population dropped in Europe because of war and famine and cold, but that people started moving into cities. And the inclusion of potatoes and corn in Europe shifted the balance. There was more food for more people, so the population, generally speaking, started to grow. So now we're going to turn to causes and philosophers and the British Royal Society, which was founded in 1660. And this is a loose affiliation of mostly wealthy men. Now, you'll recall that I added a short lecture on the question of science and work and leisure. And it's at this point that wealth, leisure, and class kind of comes into focus in the question of science. Now, it may be that what we call science, looking backward, was always pursued by people of wealth. We really don't know what kind of social structure produced megaliths or, cave paintings, but we do know that you needed an empire to administer water, and that was true in China, that was true in the New World, that was true in Rome. We know that we need engineers, we need workshops. All of these things are commanded by wealthy people. And so wealth is still important for the question of science. And here we're looking at some folks who come from the middle to upper class and have joined together for something that is also somewhat supported by the state, but now somewhat different from the state. And that's important for our story. Let's start with the right and not only learn a little bit about these three men, but also shore up our historical thinking skills, ask ourselves why these people mattered and what their lives caused. So let's ask ourselves, what is good historical thinking? We've been talking about this before, so this is not new to you. First, we need to have a reasonable grasp on the events themselves, the who, what, where, why, and when, which we can uncover by documents or oral histories or archaeology. This answers the "did it happen" question. And we also talked about 5 ways to describe significance. That's on the bottom there: permanence, magnitude, potential, quality, and net loss or negative significance. And that answers the "does it matter" question. But let's think a little bit about causality. Why is the why? This answers the "could it have happened any other way" question. And there are a number of ways to talk about causality, but there are 2 useful and simple ways to think about causes: proximate cause and cause in fact. And these are legal terms, but they're useful for historians. Now, legally speaking, a proximate cause is something that someone does or something that happens that has a foreseeable consequence without any further intervention. For instance, if an ice shelf breaks apart near a shipping lane, then there will almost certainly be icebergs floating over into the shipping lanes. No one has to think too hard to guess that that's going to happen. But a cause in fact of a ship sinking might be that the captain decided to go full speed ahead in what he believed was an unsinkable ship. You could say that it was the iceberg floating into the shipping lane that sank the ship, but we are more likely to say it was the captain's decision that was the cause. Another example, if we look at World War II, we can say that Adolf Hitler's determination to rebuild Germany into a power was the cause in fact. But we can also say that the reparations loaded on Germany at the end of World War I was the proximate cause. The Germans were tired and hungry and desperately willing to be lifted back up by Hitler. Anyone would have felt the same. So these are things that we want to think about when we're looking at something significant, like the formal beginnings of a scientific society. We might say that the cause in fact was that some like-minded guys happened to meet at college, which is true. But we can also say that the world had changed in profound ways. Proximate causes can be lined up for consideration. For instance, ideas could be printed. Roads allowed booksellers to travel. War had fragmented previous religious solidarity. Cities could shelter dissenters, and populations were slowly growing and moving into cities. If you want to do a thought experiment about proximate cause and cause in fact, you can ask yourself why Facebook took off when it did. In the last lecture, we took a quick look at Galileo, who developed and moved forward theories about motion. He moved theories about motion that other people could test and were invited to test. He used pendulum clocks and telescopes to investigate the world around him. Now, Galileo lived in Florence, and he went to the University of Pisa, where he majored in mathematics against the wishes of his father, who was a musician. Galileo believed that nature could be explained through the experimentation which could be noted in mathematical equations. Now, he obtained a chair of mathematics at Pisa, so there, Dad. But then he had some trouble and he had to move to Padua. Over the next 20 years, he experimented with falling bodies. He discovered and articulated 2 important laws of physics. First, that the distance a body falls is proportional to the square of the elapsed time that a body falls. So, in other words, if you can measure the time, you can measure the distance. Second, he also proved that a projectile follows the arc of a parabola in flight. Those are 2 things that Galileo established for the scientific world. Now, a distant proximate cause of every scientist in trouble with the authorities is the invention of movable type. Without the opportunity for wide publication, we really cannot be afraid of the speed and spread of new ideas. When you do have an opportunity for wide publication, there can be the spread of new ideas quickly. So Galileo's physical discoveries did cause a little stir at the universities. He was in trouble with Aristotelians, but they didn't cause him trouble with the authority in his world, the Catholic Church. A real cause in fact of Galileo's getting in trouble with the Catholic Church was his publication of the Dialogue Concerning 2 Chief World Systems. He made fun of the Pope in that, and that caused him trouble. Another cause in fact was his observation of the moons of Jupiter, which confirmed, in his mind, that Copernicus's conceptions of orbits was right, that the moon orbited the Earth and the Earth orbited the sun. This is his actual telescope. It's a small, slender, almost inconsequential thing. It is, however, the proximate cause of many future developments. Now, there's a wonderful documentary by Neil deGrasse Tyson. It's called 400 Years of the Telescope, and I recommend it. You can buy it on Amazon or you can watch it for free through the library, and I include some instructions in the notes for getting there. Like Galileo, Descartes was among those who were born before the 30 Years' War and lived through it and a bit after it. The 30 Years' War devastated the Church, devastated Germany, France, Spain, and the northern countries, exhausted people's tolerance for religious war, and set Europe on a path for secularism. Now, Descartes was considered one of the founders of scientific thinking and philosophy. We can say that the 30 Years' War is the proximate cause for many scholarly-minded people not seeking to become a scholar in the Church. Descartes was born in France to a middle-class family who sent him to a Jesuit college. The term college is a little confusing. This school was more like a high school. So from the age of 10 to 15, René learned Greek, Latin, and classical philosophy, which is a lot for a teenager. He then studied to become a lawyer, but he never practiced law. Instead, he chose to become a soldier in the 30 Years' War. Now, Descartes didn't let soldiering stop him from thinking. At one point during his military service in 1619, he had a series of dreams that made him decide that he personally would reform the philosophical basis of thinking. It's kind of interesting. I didn't know that until I'd done some research for this class. And we'll see that dreams also affect Mendeleev later on. Anyway, in Descartes' quest, he decided that he would ask himself what the foundation of knowledge actually is. So his statement, "I think, therefore I am," cogito ergo sum, and that he made in his 1637 book, Discourse on Method, that statement suggests that the mind is the foundation of all knowledge, and it is the proof of our existence. That is, while you are wondering if you exist, there must be someone doing the wondering. In addition to philosophy, Descartes added significantly to the study of mathematics. Early on, he discovered a line between analytical geometry and algebra. And I'm going to just quote this directly here. The fundamental insight that makes analytic geometry possible is the technique for describing lines of all sorts by using mathematical equations involving the ratios between lengths. Descartes considered his algebraic techniques to be a powerful alternative to actual compass and ruler constructions when the latter became too intricate. In other words, he figured out a way to put geometry into algebra. And when in the 19th century algebra and analysis took precedence over geometry, these rectilinear coordinate system of algebraic geometry came to be called Cartesian coordinates. And we've all heard of Cartesian coordinates because, well, maybe we haven't, but if we haven't, we should know about them because Cartesian coordinates allows a thinker to move between geometry and algebra, between physical space and a formulaic way of solving problems, and it is the foundation of our GPS. And I put a link into that particular piece of information, how they were developed and how they underscore GPS. Now, Descartes died in Sweden of pneumonia. The Little Ice Age, which we mentioned, the fact that he lived in a much colder climate than we do, didn't cause his death. Moving to Sweden didn't cause his death. But deciding to work for a patron and having a patron in Queen Christina of Sweden who lived in a large drafty castle and who wanted her lessons at 5 a.m. almost certainly caused him to catch the cold, which hastened his death. Getting pneumonia did actually cause his death. So the castle burned down in 1697. We just have a sketch of it now. But using GPS, that red dot is where it was and where Stockholm Palace is now. And that's where Descartes passed away, and we can find it because of his inventions. And you could say, actually, from the story above, were Descartes' dreams the proximate cause of you and your Google Maps? Okay, moving on. We're here at Leibniz. Gottfried Wilhelm Leibniz, and we have to pause. Leibniz is actually like Da Vinci. He's bubbling with ideas. He's an amazing man. He tried everything. He made contributions in the fields of computer science, philosophy, psychology, language, intercultural studies, religion, and technology. Don't be put off by that wacky-looking wig. He really is an outstanding man, and as far as invention and intellectual reach are concerned, he's almost alone. One of his core ideas was that he could heal the breach, personally, could heal the breach between the Protestants and the Catholics. And we can reasonably say that the 30 Years' War is a kind of proximate cause in much of his life efforts, travels, and thinking. Since he served as a diplomat, a librarian, and a historian, and he was sent on missions to validate various political claims, He was constantly dealing with the practical effects of little nations at war with each other. He was an optimist, in the sense that he thought that this world had to be, in conception, the best of all possible worlds. Otherwise, God would have made it differently. It's one kind of avenue for logic to land in, and it's a position that Voltaire later on disagreed with and made fun of in a novel called Candide. But Leibniz was no fool, and he made contributions to all kinds of things, and he, as I said, he was a Christian philosopher and polymath. He was a really fierce thinker on the subject of math and motion. Like Descartes, he was concerned with primary units, and like Galileo, he wanted to understand how to think about motion in order to understand and predict the natural world around us. Now, his version of calculus notations is the one that won the day, even though his colleagues in the Royal Society declared that Newton had thought of calculus first. Newton and Leibniz were at odds with each other over calculus. Now, calculus is, among other things, a way to calculate the rates of change, including the orbits of planets and the motion of fluids. Those two problems, the motion of planets, the orbits of planets and the motion of fluids, have dogged thinkers and practitioners already that we've talked about, the Romans, the Chinese, the Maya, right? Everybody's thought about this. Everybody's tried to figure it out. Leibniz was one of the few people to really genuinely make some progress on these things. Now look forward for a minute. Mechanics, which is the study of bodies at rest under force and bodies enacting force on each other, becomes eventually the study of gravity, electricity, and magnetism. They're just around the corner for us. So if we ask, what's the size of the smallest body that can take force and exert force, then that question of the smallest body gets us to the question of the nature of the atom, and then later to quantum mechanics. And Leibniz was a founding thinker in all those things. But this here, what you're looking at right now, is a reproduction of something he designed, which is called a stepped reckoner. It's a machine for doing addition, subtraction, division, and multiplication. The basic gear inside was invented in 1673 by Leibniz. It was used for 300 years until the electronic calculator was invented. So the kinds of problems that Leibniz were solving are the problems of his world: gunnery, navigation, planetary observation, and also trade. Now let's turn to the Royal Society. When we talked about the three European thinkers who are in the pantheon of science, we considered what caused them to live and die and work in the way that they did. We talked about causality. When we talk about the Royal Society, we'll think about their significance to the story of science. In 1597, a wealthy financier named Sir Thomas Gresham, who created the Royal Exchange, which was a place for high-end, royally licensed commerce, when he died, he founded a college with his money. It was called Gresham College, and his idea was to give lectures to the public. He funded 7 professors in astronomy, divinity, geometry, law, music, physics, and rhetoric. Robert Hooke, above, was appointed a professor of geometry at Gresham in 1664. Christopher Wren, the famous architect, was appointed a professor of astronomy in 1657, and he'd been at Oxford previously. Then Robert Boyle there on the lower left was resident of Oxford University between 1656 and 1668, and he was a friend of Christopher Wren, and he was a friend of Robert Hooke's. They all started meeting to discuss physics, math, and the natural sciences. So the connection on the left there is between Oxford University and Gresham College and Christopher Wren, the famous architect. He's not pictured here. But then these men formed a private society to pursue science. They were interested in meeting weekly, they shared experiments and reports, and they were formed formally in 1660, requesting the patronage of Charles II. And there on the in the right we have Denis Papin and Sir Isaac Newton, and they were early members of the Royal Society. Papin was in particular an instrumentalist, and Newton was a mathematician and also worked on calculus and optics, among other things. We'll talk about gravity as well. So just reminding ourselves, we're going to be talking about significance in this next series. Robert Boyle is typical of the group of men in England who formed the core of what we call the formal scientific revolution. He was an elite from a very wealthy family and, in fact, the 14th child of the first Earl of Cork. He had an estate in Ireland, and he got a very good education in England and abroad. He wrote ethical and devotional religious tracts, but he also fell in love with chemistry, and while he studied at Oxford, he gathered a group of like-minded friends who studied the effects of air and pressure independently of any curriculum they were offered. He's one of the founders of modern chemistry. Boyle's law describes the relationship between pressure and temperature and the volume of a gas. It's one we all learn today in any physics class. His discoveries had a significant permanent impact on the field. When you are finished with this lecture, you can have a look at the video which shows you an example of an air pump, and that's linked in the notes. What Boyle was seeking and didn't answer was the question that thinkers had been chasing since Aristotle. What is air? What is in air? This is a question that Boyle pursued with the help of Robert Hooke, pictured here. Hooke is well known for his book Micrographia, which is filled with sketches of the first glimpses of microscopic life. Hooke started out as an assistant to the Royal Society. The son of a clergyman, Hooke went from Westminster School to Oxford, and there he met men whose careers he would make possible. His significance lies in the quality of experimentation he made available to others. He was a skilled instrument builder and designer. Hooke was the professor of geometry at Gresham and the curator of experiments for the Royal Society. His job was basically to run the weekly demonstrations. And among his most famous contributions was this book of drawings of things he saw under the microscope. He's responsible for the universal joint, the iris diaphragm, and several other significant improvements on timekeeping, plus this picture of the flea. You know, few people had ever seen anything up close like a flea or plaque or, hair or sperm or what lives in a drop of water. After these first illustrations were published, people really looked in wonder at the hidden world that was with us all along. Now, Galileo used microscopes, but the more famous explorers are a Dutchman named Anthony van Leeuwenhoek and, of course, Robert Hooke. And both of these men lived in the generation after Galileo. This instrument, the microscope, had significant future potential. It shaped what biology could become, and it opened up a whole new world of living beings. Another important contributor is Denis Papin. If we think about the instruments we just looked at, the air pump didn't necessarily have practical applications immediately, nor did the microscope. But there were some practical problems that these early scientists did address. One was the problem of pumping water up out of mines, so mines could be entered safely. And once again, we see the problem of water management is a central concern for technology and for science. In general, although simple machines had been hooked into water flow for millennia, people were beginning to think about creating engines for work using new sources of energy. Denis Papin was the inventor of the pressure cooker and also a bone digester for cleaning anatomical specimens and cooking, and the paddle wheel boat. He was born in France, came to England, and was captured by the work of the Royal Society and stayed. Just take a minute to read this advertisement. Papin advertises a machine that can soften bones, make candy, do chemistry, make drinks, dye materials. It's a mechanical wonder. More seriously, think back to Leonardo's letter to the Duke of Sforza. No one's going to promote you if you don't promote yourself. That said, this machine has all the elements of steam engines. It had a huge effect on an entire class of machines that were subsequently developed to do work for us. Finally, Newton. Newton is covered extensively in our textbook, so I'll just review a few things here. Like his contemporaries, he lived during the English Civil War. The end of that war brought back Charles II, the son of King Charles I, who had been executed. If you're Charles II, the son of a murdered king, you're perhaps not willing to trust anyone exactly, but you do need to be involved with the upper class. The newly formed Royal Society asked Charles II to be their patron, and he agreed. Newton was the president of the Royal Society, and he presided with great seriousness and honor over the work. He was a great mathematician, and also, like his predecessor John Dee, he was an alchemist. Newton and his contemporary Boyle were also both devout Christians, and they both believed in observation and experimentation. In his own day, Newton was considered significant for Principia, his book on mathematics. More significantly, his formulation of the laws of gravity and optics are with us still. In an instance of negative significance, Newton is also remembered for trying to undermine Leibniz as well as other colleagues, and for being unwilling to share the honor for the development of calculus. This is the diagram from Newton's notebook showing that he separated light into its component colors and then ran them back through a prism to unite them again. What is air? What is light? What is everything made of? These are questions that these men tackled not by a logical theory or even by developing a balanced picture of the world, but by experimental observation. We've reviewed 7 influential men who founded what we think of as the modern scientific revolution in Europe. The first 3 are Galileo, Descartes, and Leibniz. They are, respectively, from Italy, France, and Germany. Then we looked at 4 Englishmen, one who was a French refugee, who helped found science in England: Boyle, Hooke, Papin, and Newton. Together we think of them as the founders of modern science, and it's a good and reasonable list. They were mathematicians, experimenters, technicians, philosophers, and writers. But I'm going to end this lecture with 2 people who, even in the early days of science, struggled to get a seat at the table. The first is John Harrison, a working-class maker of watches and clocks. One of the big scientific problems of the day was longitude. Sailors generally, not always, knew latitude, but they couldn't find their longitude. An accurate clock is one tool that can be used to determine location, but no one could figure out how to make an accurate clock that traveled at sea through the ups and downs of a sea, how to keep something ticking steadily that doesn't have a stable surface. Well, the lack of longitude made for horrific mistakes. In 1707, more than 1,400 sailors lost their lives in this silly disaster when a British fleet mistook its position and 4 ships grounded on the rocks off Scilly Islands and the entrance to the English Channel, as more people died in that accident than died in the Titanic. The government responded with the Longitude Act of 1741, the English government, which provided a large prize for anyone who could determine longitude accurately at sea. Now in 1762, John Harrison made the clock that won the prize, but because he came from the working class, he had a long fight for recognition. They just didn't want to give it to him. It wasn't until 1773 that King George III stepped in and Harrison was fully paid for his invention. Laura Bassi is significant as the first woman professor. If you think back to our 2 terms for causality, proximate cause, and cause and fact, you'll know that figuring out why someone was the first is difficult. What made one person step out of the crowd? Was it inevitable that someone would? Why was it Laura Bassi? Bassi started ardently as a younger person. She was supported by Cardinal Lamartine, who then became Pope Benedict XIV. She gave a public defense of her dissertation in front of the whole city of Bologna, and she was the first woman to get a PhD in physics and then to become a professor there. She was married and she had children, and she was allowed to give lectures and do experiments at home. She was the first salaried woman professor, as far as we know, in the world. She taught for 28 years. She was restricted from giving as many public lectures as men were, but she was expected to attend public functions. She fought for recognition and further appointments, and some of which she finally got when she was 65. Her teaching focus was Newtonian physics. She did experimental work with her husband, who was a research assistant in electricity, following the research done by none other than Ben Franklin. Even as women and workmen are being reluctantly allowed to the table of science, so, too, the public is finding a way in. As the century progressed, wonder and showmanship were placed at the heart of the new scientific endeavor. There is a wonderful video which introduces you to the painter Joseph Wright of Derby, his subjects, and the instruments that Boyle and Hooke used. It explains how the public engaged with early science, and you can watch it. I've got it linked in the notes. Looking forward, we will have a look at the discovery of oxygen next week and we will ask ourselves how we decide who is first.